Okay, thank you for that amazing introduction. I feel like I want to basically pause by saying I have a dog, basically a puppy, and every now and then he gets involved in the presentations with me. So I apologize for that in advance. Um, as Matt has already kind of hinted at, the web right now is a kind of very flexible and growing ecosystem, and it's kind of very hard to kind of understand what's going on. Hence, this whole notion of a wild, wild west. And a lot of what I'm going to talk about is how do we tame that. Uh, it's no surprise that web performance is crucial. I think we've all seen a bunch of these articles about how web performance is tied to revenue. Web performance is tied to kind of location in the search index, which is also a proxy for revenue. And now that we're all working from home in our garages, web performance has kind of gone from like, it's kind of okay to I really need the web to work. Otherwise, I will not do anything today. So it's very, very crucial. And it's given this, it's no surprise that there are a lot of these papers coming out improving web performance, and they all kind of start to like give us interesting and good user experience. One thing that we're kind of lacking when you look across a lot of these papers is this kind of notion of when do these optimizations work well or not. I think you pick your favorite optimization. Mine for a while was FlexiWeb, and you kind of look through and you'll see that the actual compression or the so yeah, let's go to compression. The exact compression techniques, they vary based on maybe device characteristics or network conditions, and the benefits you get is also somewhat tied to the web page structure. So you can't actually look at any of these optimizations in isolation. You need to understand under what conditions. When I say conditions, I mean network, device, or web page structure. Under what conditions do optimizations excel, and under what optimizations do you kind of get meager gains. So this is something that we need to actually understand before we start adopting and co-opting a lot of these optimizations. And right now, it's not that easy to understand this, and it's not easy to understand it for one optimization. And it's even harder to understand this for a whole bunch of optimizations together. And it's hard to understand for a lot of these optimizations because you actually need to go deploy them, test them out, and kind of understand the result. And that is very cumbersome and very, very time consuming. And to illustrate why this is crucial, we have a couple of these motivating figures. The first one is we kind of looked at one of these papers and we explored the benefits you would get across different set of websites. So if you look at the top 100 versus the top 150 versus the top 100 sports and news websites, you kind of see that the performance, like the median, is roughly the same, but the kind of tail end of performance gains from this one optimization we're looking at actually varies. So you look at any of these optimizations, and what you see from analyzing 100 or 1,000 websites is kind of a small fraction of the global picture. And it's kind of hard to understand this global picture. And I think you kind of look at the opposite end of the spectrum. If you start to combine a bunch of optimizations together, it's not really clear what the end result is. Obviously, the end result is going to be some improvement. The question is the end result going to be an improvement that is A plus B, or is it going to be log n of a plus b, or just max of a plus b, or min of a? Hopefully it's never min of a plus b, but you don't really know what happens when you start to combine these optimizations together. And as I've mentioned, um, each of these conditions, the device, network, or web page structure, is crucial. And we've actually seen in papers talking about this. In IMC last year, we saw a paper comparing landing pages to non-landing pages and showing that the structure is fundamentally different, which means the actual optimizations you might want to pick for one will vary from another. And as I said, we looked at FlexiWeb, where it kind of shows that you need to determine what compression to use, when to use compression based on network conditions. And in IMC a couple of years ago, we saw a paper kind of looking at device characteristics, so CPU resources. And there's another paper in this session looking at memory resources and their impact on web page time. So it's very hard to understand what impacts and what optimizations actually work well or do not work well under a bunch of these different conditions. And so a lot of what we've been looking at is how do we try and demystify this basically try and shed some light on the optimization landscape and try to determine and characterize under what conditions some of these optimizations work well or do not work well, and when do they compose together or not compose together. And kind of more broadly, the statement, the kind of like vision statement we have is trying to develop some technique that provides holistic comparisons of different optimizations and allows us to kind of drill down into why the benefits exist, and also to kind of understand on the other side why their benefits are not as we expected. So what attributes of a website, a device, or or the network actually leads to better or not expected improvements. The vision we have is essentially it's essentially you get a model of your optimization. So let's say, you know, a red optimization for JavaScript, you kind of compare the pages with and without your optimization. You kind of get an idea of, okay, this is my model. And then you can kind of take a look at perhaps some random other optimizations, say um, minification. So you kind of take a look at this blue minification optimization, kind of compare web pages with and without, and you see what the improvements. And this kind of creates some abstract model. And given any arbitrary abstract model, we want some amazing framework that allows you to specify what conditions, devices, and structure you want to explore. And then it kind of maps out where or what kind of combination of these conditions does the blue optimization work well versus the red optimization. So this is kind of the high level pipeline that we're working towards. You basically bring your own model into this framework, and then you specify some of these conditions you're interested in, and you kind of get a characterization of when your model performs better than another model. And you can also kind of potentially get a characterization of when both models perform well or do not perform well. So this is kind of the high level vision that we have. And I think a lot of you guys that have been working in this space for a while will kind of start to have a gut reaction in terms of, okay, awesome modeling framework. This is good. But a lot of modeling that exists today have key limitations. So in general, when you think about modeling and you look across the ecosystem, you see two broad techniques. The first is kind of empirical analysis, and this is going towards things like WPROF. And I'm a huge fan of them. They allow you to essentially extract and understand how the web page and optimizations interact with each other. Um, One key problem here is you basically have to explore potentially every combination, which is time consuming and in some cases can be kind of hard because trying to get different source repositories working together is not always as easy as it sounds. Um, so there are some these limitations where it's time consuming, just cumbersome. But on the bright side, if you can somehow overcome a lot of these limitations, you have extremely high fidelity when you're using these kind of empirical tools. On the other hand, there's kind of the more cleaner approach where you analytically model the browser, the optimizations, the web pages, the devices. Basically, you model everything. And we've seen this in Cloud Prophet, Web Prophet, and a whole bunch of other approaches right here. And one of the things that comes up whenever we look at these models is they do not always capture all of the intricate interleavings that occur in the browser. And these models are kind of overfitted for perhaps one optimization. So you're looking at you're looking at a model for trying to understand energy on mobile phones, and that model kind of overfits for that. It's hard to kind of easily generalize this, look at web performance with arbitrary device types or arbitrary network conditions. So on one hand, you have something that generalizes, which is the empirical approach, and it's very, very cumbersome. The other side, you have something that's clean, very easy to kind of think about, and very kind of easy to perform a whole lot of experiments. But on this side, you kind of lose fidelity. And as you start to look at different optimizations and these different dimensions, the fidelity that you lose either gets compounded in some dimensions or gets reduced, but you have uh, very few recourses to kind of limit and control how much fidelity is being lost across a bunch of these dimensions. So both of these approaches have their clear benefits and their clear drawbacks. And as any kind of good systems researcher, whenever you come across something like this, the answer is basically combine the best of both worlds and try and find a way for it to work out. And that's essentially what our system does. It basically tries to combine the best of both worlds. And to kind of understand why and how this works, I need to kind of take a step back, take a look at what the web page structure looks like and what um, the web page load actually looks like also. So whenever you're loading a web page, you have a whole lot of these objects. It doesn't matter what the objects are for this talk, but you have a lot of objects, and the objects are different in terms of what they are. So you have HTML, you have JavaScript, and this figure right here just kind of has color coding for different types of objects. And each of these objects basically gets analyzed, parsed, executed, rendered by the browser. And whenever we look at these web optimizations, one thing you'll observe is they actually focus on specific objects. So you look at, prophecy, and it's kind of looking at CSS, JavaScript. You look at um, transcoding, and you're focusing on images. You look at minification, and you're potentially looking at CSS or JavaScript. But basically, you start to look at these optimizations. They focus on objects, and they focus on specific processing phases of the object. They either they focus on the parsing phase, the rendering phase, they focus on like the network transfer phase. So basically, at an abstract level, a browser has a bunch of these functions. Each set of functions targets different objects, so different colored boxes. And the whole goal of an optimization is to speed up one or more of these functions. So it's kind of a nice, clean way to think about this. Given this kind of clean way of thinking about things in terms of objects, functions, and speed up of object and specific functions, then you can start to create analytical models of an optimization. You can look at the base web page without the optimization, and then one with the optimization, focusing on the function that is getting modified. In this case, it's kind of the network processing function that's getting sped up. And you can extract out the optimization as a numerical speed up value. And this is the key to a lot of what we end up doing, is basically trying to capture optimizations as speed up functions. I'm going to jump ahead. So this is basically analytical modeling. We were looking at a bunch of these optimizations and the web page structure, and then we're essentially capturing each of these optimizations as a speed up. And as I said earlier, analytical modeling is limited. It doesn't actually allow you to capture intricate interleaving. It doesn't allow you to actually provide high fidelity model. So I said this was bad, and thus far, a lot of what I've been arguing for is exactly this. And the way we overcome this problem is we have the model that's analytical model of speed up, and then we basically, instead of actually analyzing this model in a vacuum, we apply this model to an actual browser. So we basically apply this models to Chrome, and this allows us to empirically analyze the different speedups and how they essentially interact. And there are tools out there that allow you to basically explore speedups of code. So there's causal profiling, which showed up in SOSP, I think 13, and there's kind of causal profiling plus, which showed up in Sigmetrics a couple of years ago, that applies causal profiling to the web. So that is kind of our starting point. We're going to analytically capture an optimization as a speed up, and then employ that speed up into the browser to try and understand how this optimization actually works in practice. And then we can kind of vary the devices that the browser is working on, or we can kind of vary network conditions that the browser is essentially working on. And this will allow us to explore different optimizations kind of on a fixed platform. And we can also try and start to look at combining different optimizations together, which I'll talk about in a little bit. So this is kind of where we're going. And at a high level, as I said earlier, we're bringing a bunch of these techniques together. So basically bringing the best of empirical analysis with analytical model. And this is kind of similar to what happened recently, where you kind of brought the best of both worlds, and we kind of went away from the dark ages. So a lot of our framework is similar, bringing these two together and trying to move us forward. And there are a couple of challenges in trying to bring them together. First, you look at causal profiling tools. They really only speed up the application, in this case, the client-side application, the browser. So now you have to worry about, how do I speed up things that happen on the network? How do I speed up things that happen in the server? You start to look at a lot of these tools, and their initial use case is basically to understand what happens when you speed up a specific function. And in our context, we don't just care about speeding up a function. We want to speed up a function when it runs JavaScript, or we want to speed up a function when it runs jQuery. So we actually want to have fine-grained control over the speed ups. And we also want to be able to do a lot of different speed ups at the same time. You look at existing work in causal profiling, and you're just doing one speed up at a time. It's kind of, what if I sped this up? What would happen? Here, we're basically saying, what if I apply two things together or this web page? So now I need a bunch of different things to get sped up. And these two kind of bring together some challenges. I think at a high level, trying to address these challenges isn't um, it isn't non-trivial. It becomes a little trivial because it becomes a little non-trivial because we want to basically address both of these and still allow our system to operate quickly and efficiently. So our kind of combination of these results in, if you kind of look on the right side, we have a web cause, which is basically extensions to causal profiling on Chrome that allows us to speed up different functions at the same time and to do this selectively based on the object that they're processing. We've kind of added a web replay based proxy to the framework. So WebCause interacts with a network proxy, and network proxy allows us to control network speedups. And we can actually start to think about also doing server-side speedups at the network proxy. So basically, we've been using Mahi to get this network proxy integrated into Chrome, or I rather interacting with Chrome. And in terms of trying to figure out how to deal with speedups and how to deal with selectivity in terms of the granularity at which speedups are applied. One thing we've kind of done is we've basically, in the model generator phase where we're analyzing traces from Chrome to determine what to speed up, we also kind of capture functions that are being used by Chrome, which is something that Chrome naturally spits out in its devlog traces. So by capturing a bunch of this extra information in the model, we can minimize the amount of additional code that we're adding into the browser to actually to do checks and to actually determine when speedups are necessary or not. So this is the high level. Basically, you have your website, you run it with and without the optimization. You get a bunch of these devlog um, logs. We run it through our model generator, which basically extracts the speedups. It also kind of extracts which functions the speedups are being applied to, when they're being applied to. And then these speedups basically get sent to the network replay to and also to the web browser that's been augmented with causal profiling. And then we're able to basically instrument arbitrary speedups for arbitrary functions based on this workflow. And I think I wanted to kind of re-highlight two things. One is having these independent speedups and kind of um, having them be selective. We're able to kind of minimize and reduce the overhead on the browser and the browser empirical processing by actually taking extra information out of the dev tool logs that we have created by Chrome. And one of these cool things is you look through the logs and there's a whole lot in there. And so there's actually a lot of additional information we can extract and use this information to try and avoid performing additional checks in the browser and trying to perform a bunch of additional dereferences to figure out what are the right checks to perform. And this is something that I'd love to kind of discuss in more detail. If anyone has some questions, we can kind of take this in the Q&A session or take it offline. So there are a couple of these open challenges that we're actively working on right now. One of the key visions that I kind of stated is we want to be able to kind of compare a bunch of optimizations. And as I showed earlier, optimizations aren't necessarily a strictly linear addition of each other. And so this question of how do we actually compose optimizations is a crucial and open question for us. I think one of the insights that we've had is kind of going back to the web page structure and the object. Optimizations either operate on the same objects and the same kind of functions for those objects, or they don't. When they don't, it's kind of straightforward to try and compose optimizations together. When they do operate on the same objects and functions, then there's this question of, okay, should it be a strict addition? Should it be a min? Should it be a max? And we're working on a bunch of these domain-specific operators that allow us to try and merge these overlapping phases together. So this is one thing that we're actively working on. How do you actually compose optimizations together? And this is in particular challenging when the optimizations actually operate on the same functions of the same objects. Another one that we've been looking at is basically how do you express device models. I think abstractly we all think of different devices as varying levels of CPU frequencies and CPU speeds and memory. But one thing that you start to observe if you jump into a mobile phone is you have a bunch of this device-specific accelerators or DSPs. And the question here is, how do you actually model speed ups that will arise due to these optimizations? And once again, here we have this insight that these accelerators operate on specific type of object. And if you're able to identify what those objects are, and you're actually able to kind of profile the accelerator, you can kind of get a sense of what are its speed ups. And I keep saying if you are able to capture it, this is kind of tricky and challenging because this is not something that's 100% directly exposed by Chrome Dev Tools. You actually need to go in and make a whole bunch of changes to try to externalize a bunch of these things. So there's this question of how do you actually capture um, the accelerator impact on the object level, on the function level. The last open challenge kind of goes back to one of the first things I talked about. Different websites will actually lead to different notions of performance speed up. So if you analyze your optimization on sports websites, or you kind of explore it on landing pages of search engines, you'll get different values. And so one question is, what is a representative benchmark that allow us to perform an apples to apples comparison of a lot of these optimizations? And so here, as with any benchmark, the goal is something that's small but representative. And this is quite challenging because the web is constantly evolving and the web is actually quite fragmented. So you don't necessarily want just one benchmark, but you want a different set of web bench, a different set of benchmarks. For example, one for landing pages, one for non-landing pages, one for progressive web apps, and you probably also want time versions of these benchmarks. And there's been a whole lot of work in understanding web complexity, different dimensions that impact a web performance. And so we can kind of fall back to some of these papers and get a sense of what are the dimensions of interest. We can get a sense of what are some of these categories. And here the open question is, how do we actually take existing clustering techniques and tailor them to our use case? And there's a whole lot of work in terms of trying to port clustering techniques over. And this will be kind of good foundational work in terms of how do we actually create our benchmark. So there are a lot more open questions that we can kind of discuss offline, but I'm at this point probably running out of time. So to summarize, web performance is crucial. We're basically all working in our garages and we're all glued to the web. And given its importance, there's this question of how do we actually systematically understand the implications of changes that we're making. And we have proposed one framework that tries to capture optimizations as speed up functions and empirically applies them to browser code. And there are a lot of open challenges and questions that we have yet to solve. And so we're kind of looking forward to trying to solve a lot of these things. And with that, I will kind of conclude here and leave the floor open for questions.